What is generator voltage control mode? In AVR, automatic voltage regulator of the generator, here in this info page, voltage control, actually these are the modes available in automatic voltage regulator AVR panel of the generator. So today's video will cover what is voltage control mode of the generator and what are the impacts, and how does it impact on other generator terminal voltage or the grid. We will discuss in this video. So this is a generator and this is generator bus. There is another bus in between. This is generator step up transformer, and here it's a grid. Okay, now let's define the parameters quickly. Let's say this is 400 kV, this is 400 kV 400 kV bus. This transformer, before that this is the generator. Let's say the generation voltage, what will be the generation voltage? Let's say this is 300 megawatt or maybe 600 megawatt unit. 600 megawatt unit, the generation voltage is 22 kV, power factor 0.85, let it be there. This generator is kept at voltage control mode. So this is 22 kV. This transformer rating, this is 600 megawatt plant. Let's say this is 800 MVA transformer. Let's consider typical Z value and X by R. Principal tap or the nominal tap, grounding, grid side star grounded, generator side delta. Okay, done. Now this is 600 megawatt generator, 0.85 power factor, so Q max 371.847. This is the maximum reactive power the generator can generate. This is minimum reactive power minus 197.21. Okay, let's return back to the voltage control mode. So now the generator is in voltage control mode and rating 600 megawatt, generation voltage 22 kV, power factor 85% means 0.85. Real power generation is defined as 600 megawatt. Q max is 371 mvar, Q min is 197 mvar. Okay, so now let's quickly run the load flow. So what we can see, this transformer losses are not to be shown here. Okay, so this is the real power generation, 600 megawatt. 600 megawatt. This generator is generating 600 megawatt. Generation bus voltage is 100%. 100% is 100% is. So why it is, the first question should come into mind, why it is 600 megawatt and why it is 100%? Because the generator is in voltage control mode. Voltage control mode means we are forcing the generator to maintain the generator terminal bus voltage at as 100%, because here it is 100%. Generator terminal voltage is 100%. And why it is 600 megawatt? Because 600 megawatt I have given the instruction to generate 600 megawatt real power, so that's why it is generating 600 megawatt, right? And at the same time it is generating 14.8 megawatt 14.8 megawatt reactive power, whereas the maximum limit is 370 watt 371 mvar, but it is generating 14.8 mvar. Why? Because just to maintain the generator terminal voltage at 100%. Okay, now we will look back towards the grid here. The grid voltage is also 100%, right? So this generator is set at voltage control mode. Now if we change the input, means this is the input for the generator. Why it is input? Because this generated power is known, that means we are giving the input, so it is not the output, it should be considered the input to the generator. If we give that instruction to generate 500 megawatt only, so now let's check. Here the bus voltage is 100%. Here the reactive power generation is 14.8 megawatt. Now let's check what will happen. Yes, you can see that reactive power is changed to 8.43 mvar to maintain the generator terminal voltage at 100%, and it is now, this generator is now generating only 500 megawatt. Why? Because we have given the instruction to generate 500 megawatt. So based on the requirement, based on the real power what is defined to generate, the reactive power depends on that. This is factor 1. Now this reactive power also depends on the grid side, on this grid side voltage. Let's say it is 100%. Now at the grid level 400 kV grid, the voltage is 100%, because it is defined here, it is fixed value 100%. Now if we change to 101%, 101%, let's see what will happen. So it was 8.43 mvar, 8.43 mvar. Now you can see, instead of delivering 8.43 mvar reactive power to the system, the generator is now absorbing, because the negative symbol is there. That means the generator is absorbing reactive power minus 55.7 mvar, and the limit is minus 197 MW the generator can absorb. Okay, so we can conclude this reactive power generated or absorbed by this generator depends on depends on the real power generated by the generator, means whatever we are defining the real power to be generated by this generator. Secondly, on this grid side voltage, let's say it is 101 percentage instead of 101 percentage. Let's say this is 98% or 99%. Let's see what will happen. Now you can see the generator is supplying 136.6 MW reactive power. So that means it depends on the grid side voltage also, whether the grid side voltage is more than 100% or less than 100% or exactly at 100%. So it depends on that. This is factor number 2. And also factor number 3, factor number 3 is this transformer impedance. Transformer impedance, let's say instead of 12.5, let's say this is 16, I'm changing 16 percentage, I'm increasing the transformer impedance. So it was 136.6 MW, 136.6 MW. Now it is 114.2 MW. It is now reduced. So when generator impedance is increased, now the reactive power supplied or generated by this generator is reduced to maintain the generator terminal voltage at 100%. So this is point number 3. And really there is another factor we can consider, that is generator voltage, terminal voltage. So let's say we have defined the generator terminal voltage to be maintained at 100%. So if we want to maintain this generator terminal voltage at 102 percentage, then what will happen, we'll see. So now it is 114.2 MW, 114.2 MW. Let's run this. Yes, now it is increased 217.5, 217.5 MW. Why? Just to maintain the generator terminal voltage at 102 percentage, 102 percentage instead of 100%. So the reactive power generated by this generator is 217.5 MW. And what is the maximum capability to generate? It is 371 MW. So if it cross the limits, if it's cross the limit, it cross the limit means this 371 MW. So in that case, what will happen? This generator terminal voltage will drop. Generator terminal voltage will drop in that case, and it will try to draw. It will try to draw the reactive power, balanced reactive power from the grid side to maintain this generator terminal voltage at 102 percentage. To maintain the generator terminal voltage at 102 percentage. So in that case, the transformer tap position will play an important role just to regulate the voltage, So if you are set this AVR, automatic voltage regulator, AVR means on load tap changing. So it will automatically, it will regulate the generator terminal bus voltage. This low voltage side means generator terminal bus voltage to maintain this 102 percentage. So in that case, the reactive power will be drawn from the grid towards this generator terminal voltage. So in that case, the utility supply companies may impose penalty, because there should be a limit. There should be a limit how much maximum, how much reactive power can be drawn from the grid. So that's why utility companies will try to impose that every every generation company means whether that power plant, that generator in that power plant is capable to supply certain amount of reactive power towards the grid. Not it should not be that it will absorb reactive power from the grid. So just to maintain this generator terminal voltage, just to maintain the generator terminal voltage, the reactive power generation or the absorption from the or by the generator will be changed based on the generator terminal voltage set point, based on the transformer impedance, based on the grid side voltage, grid side voltage what is defined there, based on the generator real power, generator real power generation. So all these factors are there. So that is why this this voltage control mode in AVR, automatic voltage control, automatic voltage regulator, this voltage control mode will work in this way. Now also let's see, this is the reactive power 217.5 megawatt react, reactive power is generated by this generator, whereas this capacity maximum reactive power can be delivered as 371 mW. That is fine, but we'll see let's let's include one transmission line also here, because it's a grid means there may be multiple number of transmission lines or other, this is the grid, so many substations are connected, so many generating units are there. So maybe in between, if we model a transmission line, let's model a transmission line, and we can validate the impact of the reactive power on the generator terminal voltage. So let's say this is 300 kilometer line. Parameter is not required configuration. This is the configuration. Okay, now the impedance, we need to define the impedance. I'm using the typical values or from my experience, 0.3, 0.2. Okay, so we have modeled a 300 kilometer transmission line here. Let's go back to load flow study and simply run this load flow, and we will discuss about the result. Okay, so this is the grid. In between there is a transmission line I have modeled, transmission line impedance, this is the line. So what we can see, previously the generator was supplying reactive power, the generator was supplying the reactive power. Okay, just to maintain this generator terminal voltage as 102 percentage, and now it is absorbing 76.4 mW, because the reactive power is being generated by this transmission line here, by this transmission line. As you can see, this is negative symbol, means 125.6 mW reactive power is being supplied from this transmission line, because we have given the impedance, this is 3.3 susceptance value. Now also it is supplying 68.6 mvar. Now you can see this is now changed. It is absorbing only minus 20.4 mvar reactive power. Let's say it is generating 600 megawatt, means 100 percentage of its output, real power output. 600 megawatt is the generator rating, and it is generating 600 megawatt, means 100 percentage. Let's run this. Yes, so it is generating, it is absorbing minus, it is absorbing 20, almost 20 mvar, and the generator terminal voltage is maintained at 102 percentage. Here it is 98 percentage. Let's increase this voltage 102 percentage. 102 percentage. Here the generator terminal voltage is 102 percentage, and this generator is absorbing 87.4 mbar. So that means, once again, the reactive power generation of or the absorption depends on the grid side voltage. What is the transmission line, means capacitive effect, transmission line length. Let's say this line length is decreased to 100 kilometer. So you can see the impact. Now it is 64.3 mbar, 63.64.3 mbar, right? So these are the driving factors. Means grid side voltage fluctuation, whether it is less than 100% or more than 100%. Transmission line parameters, means the length and capacity effect, means susceptance value. This transformer impedance, generator real power or reactive power, this generator real power generation value, and also the generator terminal voltage, what is defined here. Okay, so in this video, up to this, what we have discussed, this is all about the voltage control mode. When the generator is kept at voltage control mode, these are the impacts. What we can see, the main purpose is to maintain the generator bus terminal voltage at the set value. What is the set value? We have said that terminal voltage at 102 percentage. So if it is 100 percentage, then definitely this reactive power value will be changed. Now it is minus 122.3 mvar reactive power is absorbed by this generator, just to maintain the generator terminal voltage at 100 percentage.